Hello students, so in this lecture we shall be talking about molecular orbital theory. Now the molecular orbital theory is a convenient pictorial representation of molecule formation suited to discuss electronic transition. So you can say that it's a convenient pictorial representation of molecules molecule formation suited to electronic transitions. Now this molecular orbital theory, or in short we can call it as MO theory, this assumes that orbitals to extend out and embrace two or more nuclei. So that the orbitals that extend out and embrace two or more nuclei, and the shape and energy of these orbitals can be calculated from Schrodinger's equation. Now there are certain rules for the molecular orbital theory. The first one is that the lowest energy first, the second rule is that maximum 2 pair electrons per orbital, and the third one is parallel spins in degenerate orbitals. These are the three rules. Now, the shape of some molecular orbitals is actually the space between which an electron belonging to their orbital with spread at 45% of this time. Now, the qualitative idea of their approximate shapes may be obtained by considering a molecular orbital to be made up of sums and differences of atomic orbitals of constituent atoms. So we can call this one as a linear combination of atomic orbitals. You can call it LCAO. LCAO. So you can write wave function NO is equal to psi1 plus minus psi2. These are the wave functions for atomic orbitals. And so psi square NO is the probability of finding electron in the particular state like, for example, psi H2 is equal to psi1s plus psi1s. Now the solution to Schrödinger's equation for hydrogen atom is psi x psi x is equal to function of r by a0 into exponential minus r by n a0, where a0 is equal to h cross square divided by 4 pi square m e square, and r is the radial distance from the nucleus. And Fr by A0 is the power series of degree n minus 1. Power series of degree n minus 1 in R by A0, and n is the principal quantum number. Now, A0 has the dimensions of length, and it is approximately equal to 53 nanometers, where this quantity R by A0, this is a pure number. So it implies that psi n square, it will represent the probability of finding the electron at a chosen distance r from the nucleus. Now, psi 1s is everywhere positive, so the atomic orbitals overlap. It's positive everywhere, so the atomic orbitals overlap. And it would result in increase in psi h2, and the molecular orbital of psi h2 is a simple ellipsoid. Symmetry in shape. Now, the laws of electronic charge between two nuclei act as a sort of cement keeping the nuclei together. This represents the formation of a bond called bonding orbital. So that bonding orbital is 1 plus sigma. So we have just the two 1s wave functions. So they will add up and they will form just like this. This is your anti-bonding orbital, and it may also form like this. This is 1s sigma star. This is the molecular orbital. This is the bonding orbital, BO. So for anti-bonding orbitals, psi 1s and the psi 1s, they cancel each other. And for antibody orbital, electron charge far away from being concentrated between two nuclei is the greatest. Outside them, nuclear repulsion enhanced. So when we talk about 1s sigma star, the star indicates that we are at high energy. And in anti-bonding orbital, it is not concentrated between nuclei, which happens in the case of orbital orbital, and it's found to be the greatest outside. And they are also in the state of repulsion. Now, if the molecule is homonuclear, then the midpoint of the bond between them is the center of symmetry. Then midpoint of the bond is the center this increase in 1s sigma star, if it increases, it will imply that no change in psi. Say that the increase in 1s sigma, this will cause no change in psi, and it is completely symmetrical. So it is called an even. However, in the case of 1s sigma star, it changes to 1s sigma u, where u stands for Angerad, and it is odd. However, in the case of a heteronuclear molecule, for example, you can think about carbon monoxide or HCl, etc. There is no center of symmetry, and odd even classification of orbities do not arise. No center of symmetry, and also no odd or even classification of orbitals. Therefore, 1s sigma, it shows a typical Morse curve for a diagonal molecule. So it will look something like this. This corresponds to 1s sigma, the odd one, and this 1s sigma, the even one. And the bond formation takes place here. Actually, the bond formation, this is distance and this is the energy. So another interesting thing is that there is no, this is a continuous curve, there is no minimum involved, odd one.